Yeah, so we'll start with chapter 2 today on the character theory, the basic ideas of character theory. Now, for example, how character theory can be useful. Let us look at a simple example already. We were doing the dihedral group of order 10, and we were able to predict. First of all, we need these facts that the sum of the squares of the degrees of representation equals the order of the group. We need the fact that the degree of the irreducible representation divides the order of the group, and the number of irreducible representation matches with the number of conjugacy classes. All these things we are going to prove in the next chapter on character theory. Also, we were able to predict that the dihedral group of order 10 must have four irreducible representations, two of degree 1 and two of degree 2. The degree 1 representation we found out, and we had a specific degree 2 representation, the geometrical one. We know that there's one more. What we did was we were able to take the degree 4 representation, that is, we took the permutation matrices because the dihedral group of order 10 is a subgroup of S5. We took the permutation matrices. All of them have eigenvalue, eigenvector 1, 1, 1, 1, 1, and we took the ortho complements. And the ortho complement gave a degree 4 representation, and we know that this degree 4 representation must decompose. And we saw that it cannot decompose into A times the trivial degree 1 representation plus B times the non-trivial degree 1 representation plus C times the geometrical degree 2 representation that we have. That cannot happen. So the only other, so in any case, there must be another degree 2 representation. And it must be a direct summand of this. But how to extract this direct summand? That can be quite tedious in general. I mean, you might still be able to wrestle your way through because the dihedral group is a small group and degree 4 is a small number. But you need, the point is that the realization of the missing representation can be quite challenging. It's not easy. Now, let me give you some idea. Now, how many conjugacy classes are there? We know that the elements of order 2 form one conjugacy class with 5 elements. And the identity element forms a single conjugacy class, singleton. So that means 6 elements. That leaves out 4 elements of order 5. They can't form one conjugacy class because the number of elements in the conjugacy class must divide the order of the group. So these 5 element sets, and also the center of the group is trivial. So there cannot be, the only singleton conjugacy class is the identity element. So that means that the elements of order 5 must form 2 conjugacy classes of 2 elements each. Correct. So that's how the total number of conjugacy classes is 4. Now, how does this help? Let us take the permutation 1, 2, 3, 4, 5, the pentagon 1, 2, 3, 4, 5, the vertices, and we are rotating it by angle 2 pi by 5, and that corresponds to a 5 cycle 1, 2, 3, 4, 5. Let us call it G. G squared, G cube, G to the power 4, and identity. And then this axis 1, 2, 3, 4, 5. Take a vertex and the midpoint of the opposite side, vertical line, flip 180 degrees. These two vertices flip, these two vertices flip, that single vertex remains vertex. Elements of order 2. Let us call them T. Let's call one of them T. Then we know that there is a relation like TR equal to R to the power n minus 1 T, or TRT equal to R to the power n minus 1. But T is an element of order 2. TRT means TRT inverse. So TRT inverse is R to the power n minus 1, which means what? The element R is conjugate to R inverse. R and R inverse are conjugates. So G and G to the power 4 are conjugates. They will form one conjugacy class. G squared and G cube will form one conjugacy class. Is this clear so far?
Yes.
Now, you might ask, so you got a group representation from G to GLV, rho. Now, suppose you have an automorphism of the group, lambda. Suppose lambda is an automorphism of the group. Rho composed with lambda is also a group homomorphism, isn't it? Yes or no?
Yes, sir.
Now, you might say that will give you a plethora of new group homomorphism representations. Take a given representation and compose with automorphisms of the group. Are you really going to get a plethora of representations? What if the automorphism is an inner automorphism? Automorphism is an inner automorphism. Say X or a fixed element H, X, H inverse. So you're simply looking at the so-called new representation is rho of H, X, H inverse. But there will be rho H, rho X, rho H inverse. That is just a conjugate of the original representation. You have got an equivalent representation. You have not got anything new. This is key. So inner
Yes, sir.
automorphisms, composing with inner automorphism is not going to give you anything new. What about outer automorphisms? Outer automorphisms are a different matter altogether. Now, how do you know that the dihedral group of order 10 has an outer automorphism? What gives you the hint that there must be an outer automorphism? And if there is an outer automorphism, let us call it J, then phi composed with J probably may give you another a row composed with J may give you another representative, where rho is my two-dimensional representation. Okay, the matrices wala representation. No? We got the diagonal flip and the symmetries of the regular n-gun that give you a set of 2 by 2 matrices, and we realize the dihedral group as a subgroup of GL2C. Fine. Let us call it the geometrical irreducible representation of degree 2. Now you may want to compose this geometrical irreducible representation of degree 2, call it rho composed with J. Rho composed with J. Let us call it rho tilde. How do you know that rho and rho tilde are not equivalent? If the J were an inner automorphism, definitely they're equivalent. But if J is an outer automorphism, there is a chance that they may be inequivalent and you may get your missing representation. Correct. But first of all, before you do this, you need to understand, is there an outer automorphism in the first place? For example, S3 has no outer automorphisms. S4 has no outer automorphisms. The symmetric groups SNs have no outer automorphisms. Except n equal to 6 and n equal to 2 is uninteresting. Symmetric group of order 2 is uninteresting. So from n greater than or equal to 3 onward, the only symmetric group that has an outer automorphism is S6. This theorem is called Holder's theorem. And this Holder's theorem is going to feature very prominently in chapter 3. Very prominent. What about the dihedral group of order 10? If there is an outer automorphism, which it may switch these two conjugacy classes. The elements of order 5 form two conjugacy classes of two elements. The outer automorphism may switch these two conjugacy classes, and the other conjugacy classes may remain as it is. The outer automorphism will not do anything. If these two conjugacy classes get switched, then what happens is that the most important thing about a group representation is that often the representation itself is not important. What is important is the character of the representation. What is the character of a representation? The character of a representation is the trace map composed with row. Call it chi. If row is a representation, chi sub row G is trace of row G. So take the map row which takes G to GLB, compose it with a trace map. The trace map composed with row is called the character of the representation. Character is a scalar value, C value function. Since similar matrices have the same trace, if you have a bunch of conjugate elements in a group and apply row to that, the row values will be conjugate matrices and they will all have the same trace. So the trace will be constant on conjugacy classes. It is a class function. The trace of row, the character of the representation is the most basic example of a class function. And we are going to say that if you take a bunch of irreducible representations and you take their, and if you're forming a parliament and you take the characters, if you take the traces of those, and that is you look at the corresponding characters, it will form a basis for the family of all. You've got the vector space of all class functions, and these characters will form a basis for this vector space of class functions. Now, suppose if I take two irreducible representations, then they are so they are some kind of, so what is the philosophy? These characters are the building blocks for class functions. Class functions form a vector space. It will form an inner product space. I can put in a complex inner product, which you're going to define. That's the content of this chapter. And these irreducible representations will form an orthonormal basis. And if you take two distinct irreducibles in our parliament of irreducibles, the corresponding characters will be orthogonal. So last time I mentioned, remember that if rho and sigma, if rho and sigma are two irreducible representations, and if their traces are the same, that means that the characters are the same, then those representations have to be equivalent. Because if they are inequivalent, then the corresponding characters will be orthonormal. So they can't be the same. Is this clear? What I said?
Yes, sir.
Now, let's come back to the dihedral group. If we know that, suppose if we're able to cook up an outer automorphism, what are the conjugacy classes? Singleton, let us call it C1. A conjugacy class with 5 elements of order 2, let us call it C2. Let us call the elements of order 5 forming two conjugacy classes C3 and C4. Now we have a geometrical representation, irreducible representation of degree 2. Take its character, that is, take its trace. What will it do to the? It is going to be it's going to be constant of the conjugacy class, the singleton conjugacy class consisting of identity. What will it be? Identity matrix. Identity matrix of what size? 2 by 2. But because what is the degree of the representation? 2. But what is the trace? 2. So what is the character value there? 2. And then the elements of order 5. It will take some value. And then the elements of order 2, elements of order 2 forming a conjugacy class of 5 elements, 5 element conjugacy class, some character value. And the elements of order 5, C3 and C4, and there will be this character will take some value at C3 and it will take some value at C4. Correct? Now it's trace, no? It's basically traces of those matrices. So we just have to find those matrices and write down the traces. What do you think will be the traces? What are the conjugacy classes again? G and G to the power 4, 1, and hello,
G
G squared
squared
and
and
G cubed.
G cube.
But G to the power 4 is so in terms of rotation, it is rotating through angle 2 pi by 4, and G to the power 4 will be G inverse, no? Rotating through angle minus 2 to 2 pi, so 2 pi by 5 minus 2 pi by 5. But what are the matrices? Cos 2 pi by 5 minus sin 2 pi by 5, sin 2 pi by 5, and cos 2 pi by 5. What are the trace for the both the conjugacy? It will be
1.
2 cos 2 pi by 5. And for the other one, it's going to be 2 cos 4 pi by 5. Cos 4 pi by 5 and cos 6 pi by 5. They'll be the same. And cos 2 pi by 5 and cos 4 pi by 5 will be the same, correct? Hello.
Yes.
Arey, trigonometry, bhai. So what are the value? What are the character value for the conjugacy class C3? Please tell me. 2. Arey, trace bolo na. 2 cos 2 pi by 5. And for the other conjugacy class, what is the trace? 2 cos
Uh, 2,
G squared.
4,
4
4
pi
pi
by
by.
5. They are different. These two numbers are different. These two numbers are different. Now, if your outer automorphism does the following, whatever be it, the outer automorphism is going to fix the identity element. It's not going to become identity will remain identity. So that conjugacy class will be the same. Even after applying the row composed with J, what will that do to the conjugacy classes? And singleton will remain singleton. If if the elements of degree 2 forming a conjugacy class of 5 of a bunch of 5, if that conjugacy class remains as it is, then the corresponding character value will be the same, correct?
Yes.
But if this outer automorphism switches the two conjugacy classes, C3 becomes C4 and C4 becomes C3, then what will be the corresponding character values? That will get flipped, no?
Yes.
That will get flipped. So those two characters will be distinct. Those two characters will be distinct, and those two representations cannot be equivalent. Those two representations cannot be equivalent. Correct?
Yes.
So now we must examine very carefully, is there an outer automorphism which is switching C3 and C4? Because if that is the case, then we know that our analysis is now showing that we are going to get indeed the missing representation. We're getting a realization of that missing representation. Now, how to construct the outer automorphism? Remember, G to the power 4, 1, 2, 3, 4, 5, and its inverse. So let us we know that G and G inverse are conjugate. So let us not worry about that. So let's say G only. Then G squared. G squared is what? 1, 3, 5, 2, 4. 1 goes to 3, 3 goes to 5, 5 goes to 1 goes to 5 goes to exactly 5 goes to 2 and 2 goes to 4. So simply compute G squared. Now G and G squared are both 5 cycles, correct? These 5
Yes,
cycles are not conjugate in the subgroup, but they are conjugate in the original group S5, in the parent group S5. what you do is I'm going to dictate a certain. So the G and G squared are both 5 cycles, and so they're going to be conjugate. Take this permutation 2, 3, 5, 4. The 4 cycle 2, 3, 5, 4. Call it alpha. The permutation 2, 3, 5, 4. Call it alpha. That alpha is not in my group. It is in S5. It is not in my dihedral. But I can take all these 10 elements that I have. Write the pentagon. How do you write the pentagon? 1, 2, 3, 4, 5 in that order. Then there is a 5 cycle 1, 2, 3, 4, 5. And then take its powers. Then fix one. Fix one. 3 and 4. They will get switched. 2 and 5 will get switched. So you have to do the perpendicular axis of symmetry and do this. And write down those elements of order 2. Actually, you should write down all the 10 elements. Take this alpha 2, 3, 5, 4. What is alpha inverse? 2, 4, 5, 3. Take this alpha and conjugate all the elements and see what happens. If it happens that you again get the same 10 elements in a possibly different order, then you know that you have automorphism. Not an inner automorphism, because alpha is not in my is not in the dihedral group. It is in the parent group. It's not in my dihedral group. So it's an outer automorphism. I had done the calculation, and lo and behold, the elements of order 2, which forms one conjugacy class, they remain as the alpha conjugates to the same set of 5 elements in a different order, and it switches C3 and C4. I had done the calculation. I want you to do this calculation today before you go to bed, and let me know if there is a problem. If I have the important thing to check here is, if you must conjugate all the 10 elements and make sure that it is the same 10. It should not happen that this subgroup itself becomes something else. It's a subgroup of S5. It should remain the same subgroup of S5, not some other subgroup. Right. Perhaps you can prove this geometrically also. Perhaps you can try to give a geometrical argument why this subgroup will be the same. But a simple device will be just do it. Just can it do the calculation? It's a very small number and just do it. If this happens, and if you realize that the conjugacy classes are getting flipped, C3 becomes C4 and C4 becomes C3 under this outer automorphism, then you have found the missing representation, namely rho composed with J, where J is this outer automorphism. This is clear? Now you can you will clearly start seeing that doing things by hand is going to be pretty tough. Now, after dihedral group of order 10, you will go to the alternating group of order 60, A5. It's a simple group. You're going to look at its conjugacy classes. It's going to have so many different types of representation: a degree 5 representation, a degree 4 representation, 2 degree 3 representation, then degree 1 representation. How are you going to realize those representations? Fortunately, in the theory of group representations, you don't need the actual representations themselves. Coming up, actually giving you these representations explicitly can be a Herculean task, even for specific groups like the symmetric group. What happens is, it is the characters that you really need. So Lederman writes his entire book on the theory of group. He works with characters rather than the representations themselves. Without getting into the representations, He gets information about the characters and he uses the. For example, we are going to prove the Burnside's PQ theorem using only the characters, not the representations themselves. We are just going to work with characters. So it is the characters that are more important than the representations themselves. How do you avoid actually realizing these representations? Why is it difficult to realize them? In the context of continuous groups, like the unitary group, the story is very different. You can actually write down these irreducible representations explicitly, and by using calculus. So, character theory is a next important topic, next important theme in this course. So, let me now start presenting the screen.
So before we move on, I just had a question. Like we showed that if we have an outer automorphism J, then and phi is some irreducible representation, then phi and phi composed with J will both be inequivalent representation.
Provided
So
you can prove that the characters are different. Suppose, for example, by some, okay, suppose, for example, the phi assigns the value 0. Suppose instead of assigning 2 cos 2 pi by 5 and 2 cos 4 pi by 5, somehow it happened that those two values were the same, or those two values became 0. Then even if the outer automorphism switches those, the new character
right.
will be the same, and we're out of luck. Our luck will sometimes forsake us.
So, but do we have an answer to the question that if we are given to inequivalent representations, then there exists some outer automorphism
That may not be
J?
that is not true. It is not the case that two inequivalent representations will always be obtained by this outer automorphism. What gave me in the context of the dihedral group, because two representations had the same degree, and there are two conjugacy classes which had the same cardinality, that motivates us to search for an outer automorphism which is responsible for this. The same thing is going to happen in the alternating group,
I see.
A4, in A5. See, in A5, what is happening is it has 5 cycles. How many 5 cycles are there in A5? 24 5 cycles. Can they form a conjugacy class? No, because A5 has order 60 and 24 doesn't divide 60. The 5 cycles,
Right.
they were forming the 24 5 cycles form one conjugacy class in S5. But this 24 wala
Yeah.
conjugacy class in S5, when you in A5 breaks into two conjugacy classes of 12 elements each. We are going to prove a general theorem that if you have a normal subgroup, okay, if you have a normal subgroup of G of index 2, and if a certain conjugacy class in G is contained in N as a set, then two things can happen. Either it will remain a single conjugacy class in the subgroup, or it split into two conjugacy class with equal cardinalities. Not difficult to prove. We're going to prove that. So again in A5, there are two conjugacy classes of 12 elements each. That again gives us a hint that maybe there is an outer automorphism that is responsible for that. Okay,
Yes, sir.
all right. So now let us again look at this. Maybe we can't do too much because I think that this preamble was a rather lengthy. And then let's begin with the next chapter. So, character theory. So, we look at the category of group representations. There are morphisms and certain invariants that turn out to be certain functions on G known as class functions. And these special types of class functions are called characters. These characters turn out to possess certain orthogonality properties. One is gradually led to a Fourier analysis on finite groups, analogs of the Parseval formula and such. These things constitute the heart of representation theory, and analogs for compact groups will be taken up later. Morphisms between representation. Suppose phi from G to GLV and psi from G to GLW are two representations of G. A morphism or an intertwiner or an intertwining map is a linear transformation T from V to W such that this diagram commutes. In particular, if T is an isomorphism, it is called an equivalence. So we can talk about morphism of between two um, representations. The definition is of course quite general and makes sense for any group, finite or not. The set of all morphisms between two representations phi and psi will be denoted by Hom phi psi G, which is obviously a C linear vector subspace. Set of all linear transformations from V to W is called Hom VW. And those linear transformations for which this diagram commutes for every G, that's going to be form a very small subset of Hom. It's going to form a vector subspace of Hom VW and is usually a very, very small subspace of this vector space. Schur's lemma is going to quantify this statement. What exactly is this Hom G VW? So, and then of course, if phi and psi are equal, then identity element belongs to Hom G phi phi, and morphisms can be composed, and the morphisms form a category. The kernel and image. Suppose T is a morphism between two representations phi and psi. The kernel of T, in the usual sense of linear algebra, is G invariant subspace of V. Proof is immediate. Image of T is also a G invariant subspace. So, well, suppose if V is in the kernel, we're going to show that phi G of V is also in the kernel. How do you know that? T applied to phi G of V will be psi G of TV, but TV was 0. So phi G of V is also in the kernel. So V is the kernel means phi G of V is also in the kernel. And so the kernel of T is a G invariant subspace, and the image of T is also a G invariant subspace. Next is Schur's lemma. Let phi and psi be irreducible representations of a group G and T be an intertwiner. All vector spaces are supposed to be complex, and this is a very important hypothesis that the base field is a field of complex numbers. So we got, what is the hypothesis? Phi and psi are irreducible. Irreducibility is very, very important. Okay. And you got an intertwining operator. Then the intertwining operator, this is not an iso equivalence or anything like that. I mean, there's a morphism between these then this either T must be 0 or T must be invertible. Only two options. Second, if phi and psi are inequivalent, then T must be 0. If phi and psi are inequivalent, then T must be 0. The second choice doesn't happen, the first choice happens. If phi and psi are equal, then T must be a scalar operator. Okay. So if phi and psi are inequivalent representations, inequivalent irreducibles, then the Hom is 0. On the other hand, if phi and on the other extreme, if phi and psi are equal, then the Hom is just the scalar operators, lambda times I. Remark, this Schur's lemma is going to be play a very critical role in what's going to follow. Despite its paramount importance, the proof is pretty easy. We are happy that, oh, a very important theorem but very easy proof. We should be happy. So phi and psi are representations, G to GLV and G to GLW, and T is a intertwiner. Assume that T is not equal to 0. If T is not equal to 0, then kernel of T is an invariant subspace. Correct? Kernel of T is an invariant subspace, and T is not 0, so the kernel cannot be the whole space. So kernel must be 0 because it's irreducible. No non-trivial G invariant subspaces. So T must be injective. So if T is not 0, then it becomes injective. Again, image of T is not 0, and image of T is a G invariant subspace. And so again, appealing to irreducibility of psi. Earlier we appealed to irreducibility of phi. Now we're appealing to irreducibility of psi. Image of T must be the whole thing, and so T is also surjective. So T is both injective and surjective. So if T is not 0, then it must be isomorphism. Then T must be an invertible. Okay. So again, turning to 2, if phi and psi are inequivalent, then T bijective is ruled out, because if T is bijective, then they'll be equivalent. Hence, from the first option, T must be 0. Finally, if phi and psi are equal, that is V and W are the same vector space, T is a linear operator on V. Correct? T is a linear operator on V. Take lambda to be an eigenvalue of T. Here we are using the fact that the base field is the field of complex numbers. Then T minus lambda I is an intertwining operator. T minus lambda I is not bijective, no? Because T is an eigenvalue. So the other extreme must happen. T minus lambda I must be 0. So T must be the scalar operator. Pretty easy, right? If
Yes,
phi
sir.
and psi are equivalent irreducible representation, then form G phi psi is one dimensional. As a simple corollary of the last part. We consider the vector space of all homogeneous polynomials of degree k in n variables x1, x2, xn. We have a representation of the symmetric group. Namely, take a permutation G and take a polynomial which is take a homogeneous polynomial in x1, x2, xn. Simply permute the variables, permute the arguments. You get another homogeneous polynomial. Find the invariant subspaces. Is a linear transformation T from V to V given by T P x1, x2, xn equal to P of x2, x3, da, 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 xn, x1, an intertwiner? There are some exercises. If phi and psi are equivalent irreducible representations, then phi psi is one dimensional. I think I will leave out the so phi. Okay, or maybe let's do it. Phi Hom G phi is one dimensional by Schur's lemma. Now suppose if psi1 and psi2 are equivalent representations on a vector space on vector spaces W1 and W2, you pick then equivalent. So you can pick an intertwiner. Then we have a map Hom G phi psi1 to Hom G phi psi2 given by composition. This is a linear transformation which is invertible, and the result will follow. Orthogonality. This is one of the most fundamental idea in a theory of group representations, a character of a representation. Let G be a group and rho from G to GLV be a finite dimensional representation. For each G in G, we compute trace rho G. Trace rho G. Namely, simply take rho G and follow it up with trace. G going to trace of rho G. This is called the character of rho. Among all conjugacy invariants in GLV, the trace is the simplest one because it extends linearly to all linear transformations. Trace is a similarity invariant, and so equivalent representations have the same character. The converse is also true for finite groups, and we shall look at the converse later. Defining the trace would be problematic if dimension of V were allowed to be infinite. Usually, in such situation, one works with a Hilbert space V, and GLV is replaced by the group of invertible bounded linear operators. One would have to restrict it further to something like trace class operators or something like that. The celebrated Peter-Weyl theorem says that for a compact group, all irreducible representations are finite dimensional. So defining the trace or a character is no issue for a compact group. And then let us introduce a function algebra. For a finite group G, this is a set of all functions from G to C. So it's just all the functions from G to C. In other words, it is a Cartesian product of mod G many copies of C. It's a vector space. It's a C vector space. It is a C to the power mod G. It's a finite group. So if it is a group contains 3 elements, it is simply C3. If the group contains 6 elements, it is C6. That's all. And it's a usual. There is a usual. It's a Hermitian. It's a Hermitian. The usual Hermitian form. Okay. Sometimes, not sometimes. In what follows, we are going to put a 1 upon mod G into 0.3 so that it's an average. So that the right hand side is actually an average. And in case we are going to be working with a compact group, we are going to be we are going to be looking at we'll have to divide. We'll have to work with some Haar measurements or something like that. We'll be interested. We won't be interested in all functions. We'll be interested in continuous functions. We'll be interested in L2 functions, whatever. Of course, the characters are elements of the function algebra, and the important result is that the characters of distinct irreducible representations are orthogonal with respect to this inner product. The orthogonality is with respect to this inner product 2.3, which already shows that now this already tells you that the parliament of irreducibles is a finite family. You get the first important result that up to equivalence there are only finitely many irreducible representations. In addition, we shall prove that the number of mutually inequivalent representations is the number of conjugacy classes. The degree of representation of the irreducible representations divide the order of the group, and the mod G will be d1 squared plus d2 squared plus dk squared. Okay, so I think let's stop it here, and we will continue this tomorrow.